First of all, I want to say thank you to Ivan and my colleague Alex for the invitation and the organization of this workshop. And I have to say I'm happy to be here among other interesting speakers in this workshop. So today I want to talk about some working ideas which hopefully will turn into a paper someday. And my talk will be on inconsistent scientific reasoning without an inconsistent word. So the main idea would be scientists reasoning based on an inconsistent basis, without that spilling into the world, without them believing that there are actually contradictory phenomena or a contradictory world. So, in the history of science, it is important to master the ability to work with these, let's call them temporary contradictory theories. And it's important to say, first of all, that contradictions can be informative. In juridical testimonies, for example, statements from suspects of crime, if those people are questioned and they contradict each other, then we will know that most probably at least one of them is lying, so we can get information from this contradiction. And there was a very famous example is the age of the Earth in the history of science, where different theories from different disciplines contradicted each other about a specific issue. And in this case, about the age of the Earth, there was a contradiction between geology and evolutionary biology and thermodynamics. This contradiction was later resolved after the discovery of radiation. And I'm not really going to go into the details. I just want to mention that this example exists in the history of science. Now, motivation. Can inconsistencies in science, first of all, be fruitful? Is this something worth looking into? Do inconsistencies actually exist in scientific inquiry? And first of all, what does it mean to reason on an inconsistent basis? What does this involve exactly? Then is the question, do these scientists actually sometimes work with these inconsistent theories? So if they exist, do actually scientists work with them? And if so, are they successful to do so? And if yes, then how is it possible? How do they do it? And my main issue here is I want to study these cases where there was a reasoning in the history of science using these inconsistent cases, inconsistent theories, and so on. And I want to see if the scientists actually reason rationally with these theories and work with them, and then provide an explanation as to how and why this was possible. How did they do it? What was the explanation behind this? And now I want to move to some very preliminaries, just to get it out of the way. Contradiction / inconsistency exists when a pair of propositions is contradictory when one is in negation of the other. I will say more about that later on. And I know that some people in the literature separate these two terms, like they say that contradiction is a bit different from inconsistency, and they say that an inconsistency falls into, is more similar to contrariety, which is something I will go on later. Then triviality, a set of propositions is trivial if it is possible to derive any proposition from this set of propositions, assuming, of course, classical logic, where this is possible. And this mode of explosion, a set of propositions is closed under classical logic. A set of propositions which is closed under classical logic is trivial if this set of propositions is contradictory. And propositional logic, I don't need to say anything about that, but a logical framework in which the principle of explosion does not hold when faced with a contradiction, then it's consistent. Now, I want to say a bit more on inconsistencies in the history of science. So in the history of science, some theories were inconsistent, at least at some point in their development. And for example, there are three main examples in the literature. So there are theories that are inconsistent in themselves, like Bohr's atomic theory of the atom. Many people argue that this was actually inconsistent. And Lakatos actually dealt with this specific example. And so the main idea here is that the atomic theory of Bohr assumed that the atom was following Rutherford a theory where is this thing is here. So it's the planetary systems with electrons orbiting around a positive nucleus. And the main idea for the Rutherford theory is that these atoms can remain stable, whereas Bohr also assumed the Maxwell-Lorentz theory of electromagnetism, which first of all is well corroborated, and then it says that these should collapse. So you have a situation where atoms are stable and they collapse at the same time, so inconsistency. Now, another example in the history of science is theories that are mutually inconsistent. So it's, as I said before, for the age of the Earth, theories of different disciplines were inconsistent among them regarding one certain issue, that being the age of the Earth. And lastly, when we have a theory that is inconsistent with observation, we also get inconsistency in scientific inquiry. This being Mercury's perihelion, which I will just say more about that and focus on this example now. So, this example with the Mercury's perihelion is an example of an inconsistency between theory and observation. And these are generally called anomalies, but still, arguably, they are inconsistencies. So, an anomaly is a contradiction that occurs when there is an empirical theory T that has O as an observational consequence, and after a reliable experiment, we actually observe not O. So observe negation of the observable. An empirical theory T, in other words, predicts O, however, O is not observed. After considering different explanations and calibrating the acceptable margin of error, in the case of Mercury's perihelion, scientists could not do anything about that, but recognize the observational result as the negation of O. So, in the precision of the perihelion of Mercury, which was at odds with Newtonian celestial dynamics, it was known for a long time before the rejection of Newtonian dynamics in favor of special relativity. Some people would be so quick as to render the theory as being wrong and they would immediately discard it. This is something that happens. I think Christ called those people like naive falsificationists, which the main idea being with the first example of an observation that does not go alongside the theory, then the theory should be discarded. However, I believe the theory in this case should not be discarded at least until we arrive at a better alternative. And this is why I'm saying we need to find a way to deal with these issues. Now, going to the perihelion of Mercury. Classical mechanics predicted a certain value for Mercury's perihelion, which went against the actual observation. That's the idea. And the theory predicted that the calculation would be the preserved perihelion of Mercury would be 5,557 seconds of arc per century, whereas the actual observation after calculation and experimentation, it was observed to be 5,600 seconds of arc per century. So we have the expected observation, we have the actual observation being something else. So there's also 43 seconds of arc per century discrepancy between them. And the main idea here is, as seen from the Earth, the precision of Mercury's orbit is measured to be 5,600 seconds. Newton's equation, on the other hand, taking into account all the effects from planets, as well as a very slight deformation of the sun due to due to its rotation, and the fact that the Earth is not in an inertial frame of reference. Theory predicts a position, as I said, of 5,557 seconds. So the discrepancy is obvious. Now, many ad hoc fixes were devised, such as, for example, assuming that there was a certain amount of dust between Sun and Mercury that would explain this difference. But none of these were consistent with other observations. So, for example, there was no evidence of dust. No evidence of dust was found when the region between Mercury and Sun was carefully scrutinized. So in this situation, then, these ad hoc solutions didn't occur, so they couldn't find a solution. So there was indeed a duration in time that scientists, whether they knew it, whether they were aware of it or not, reasoned on an inconsistent basis. This being the duration of the existence of the inconsistency and the non-abandonment of the theory. But then again, this did not result in the immediate abandonment of the theory. So scientists at that time may have recognized that this anomaly was there, but at the same time they didn't just push it aside and continued working on other stuff. They had in their thinking, and this is what Lakatos said, that scientists have fixed things. They don't immediately abandon theory merely because facts or observations contradict it. Now, I want to keep in mind this perihelion of Mercury example, and I want to talk about an important tangent of this debate regarding contrariety, inconsistency, and contradiction. First of all, do the terms inconsistency and contradiction mean the same, and if so, do they have the same implications? I would argue that they are not the same, but they do have the same implications and should be treated as such. And if we want to tackle contradictions one way or another, first we need to make sure that they are actual contradictions. So in the literature, some people argue that an inconsistency is weaker or is at least less serious than a contradiction. So in talk about scientific theories, if a part of the theory is inconsistent with another part, attention is drawn to it, of course, but it is not considered as serious as if there was a plain or blatant contradiction in the theory. So the main sentiment seems to be that it is just a mere contradiction, so it's just a mere inconsistency. It is serious and we need to deal with it, but at least it's not a contradiction. And I think it's important to attend this issue because the treatment or the explanation given for a contradiction in the sciences, the way we want to deal with that, depends on whether we consider the said issue as an actual contradiction or not. In other words, first we need to correctly identify the problem in order to then try and find a fitting solution or explanation for it. And here I give an example from Foley, 1979, but it says that, and of course this set of beliefs is inconsistent, it is logically impossible for all of them to be true. So far, however, there is no contradiction. So you can see that he differentiates between the meaning of an inconsistency and the meaning of a contradiction, and he says that the latter is more serious than the former. And Bézier also mentions that contradiction is often confused with contrariety, which is something that I agree with. But as I will show, the implications of these two terms in this case that I'm talking about are the same, and thus they should be treated as the same. Now, a pair of contradictory propositions, I have to say from the start, they cannot both be true and they cannot both be false. So, in other words, one is necessarily the negation of the other, whereas in a contrary situation or an inconsistent situation, propositions cannot both be true, but they can both be false. And I will say more about that in the next slide, but here I just want to say that the reason I'm dealing with with this issue here is that there is a series of papers between Decio Krause, Jonas Arnhardt on the one hand, and de Rode and Newton da Costa on the other. And the former argue that in quantum superpositions, like the multiple states of quantum system is in before measurement, that this is an example of a contrary situation and not a contradictory one, whereas de Rode and Newton da Costa argue that it's an actual contradiction. And we can see in this series of papers that the solutions devised to deal with this are different when you consider the quantum superpositions to be a contradiction or whether you consider them to be just a contrariety. And here I'm going to give an example. So consider these two statements. The house is all green and the house is not all green, which amounts to it is not the case that the house is all green. So assuming we hold the same definition of the terms involved, one proposition is the negation of the other. In other words, if the proposition the house is all green is true, then the proposition the house is not all green is necessarily false, and vice versa. In other words, simply either the house is all green or not. We cannot have both. We cannot have a situation where the house is all green and is not all green at the same time. Now consider these two pair of positions. The house is all green and the house is, sorry, it's a mistake here, described a lot. So the house is all green and the house is all yellow. In this case, there is a difference here, and we can see that. It cannot be the case that both of these can be true, so the house cannot be all green and all yellow at the same time, but both of them can be false. For example, if the house is all blue. And, and this is the main difference between a contradiction and an inconsistency, at least it's one that the aforementioned people have in mind. And the main idea boils down to, in an inconsistency, the pair of sentences can both take the value false, as I said, but it cannot be the case that they both take the value true, the truth value true, whereas a contradiction, a pair of sentences, one sentence is necessarily true and the other is necessarily false. And this is captured in the well-known square of opposition. And for me, in this talk, I'm focusing on this part, on contraries and contradictories. And what this shows is that from the above analysis, we can see that, at least prima facie, there is a difference between an inconsistency and a contradiction, and that the contradiction is kind of more serious than the inconsistency or contrary. And from this, we can see that actually people in the literature have this in mind when they say that these are different, which differentiate between them. In other words, an inconsistency or the contrary positions does not have the clear form of P and not P. So triviality from logical closure seems to not take place in the same way as it does in a contradictory pair of positions. However, here I will disagree with this. I will disagree that an inconsistency is less serious. In fact, it is as serious as a contradiction. In other words, a contrary pair of positions is as serious, it has the same implications as contradictory pair of positions. And to show why this is the case, I will be using the example from the sciences which I mentioned before, involving numbers, the perihelion of Mercury. And the reason I depart from these colors and houses is because with numbers and number theory and axiomatization, we have a clearer and more robust way to present this idea. So, back to the perihelion. We have these two positions, P and Q. P being 5,600 seconds, Q being 5,557 seconds. So, where's the contradiction here? Because these two numbers are just different numbers, so why am I talking about contradictions? At most, we can say that the observation, P, and the theory or estimation, Q, at most I can say that they are inconsistent or just different. To say that this is a contradiction seems a bit far stretched. So, having in mind what I said about houses and colors, the formulation of the sentences does not show a clear contradiction. 5,600 is not the direct negation of 5,557. Furthermore, both propositions can be false if the actual precision of Mercury's orbit is 4,000 seconds. So the falseness of the one does not necessarily imply the truthness of the other. Yes, and if the correct precision is 4,000 seconds, then the fact that 5,600 seconds is false does not imply that 5,557 seconds is true. So P and Q seem to be irrelevant in this sense between them, or let's say just different. Therefore, they do not seem to yield a contradiction when put together. However, I argue that there is a contradiction, but it's hidden. In this case, P and Q are not totally unrelated, saying that Q, 5,557 seconds, implies the following set of propositions. So saying that Q implies that not R, not S, which means the precision of Mercury's orbit is not 5,000 seconds, is not 5,100 seconds, and so on. And in this set of negations, there's also not P, which the precision not being 5,600 seconds. That is, we have the situation in which Q necessarily implies this set of things that Q is not. So, contrary, contradictory, same implication. If so, they should be treated the same. And the main idea is illustrated here. So Q necessarily implies not R, and Q necessarily implies not S, and so on. And Q necessarily implies not P. So the contradiction is there because if it implies not P, and then we have P and Q, where Q implies not P, so we can get to not P and not P. One objection is that this thing here is not a clear pair of positions in the form of P and not P. What we have is just this long conjunction of propositions. My response here would be to consider then another way to show that having a set of propositions of this sort and having not R, not S, and so on, not P, and proposition P gives a contradiction by considering the following. So, going back to houses, the house is all green and it is raining, so we add this conjunction here, and the other position being the house is not all green. Even though the first sentence is a conjunction, still we can see that there is a contradiction taking place. The mere appearance of a conjunction, so the mere appearance of rain here, the addition of a further element in one of the two propositions, does not change the fact that contradiction is still in place. So the addition of rain does not change anything about the house being all green and the house not being all green. So is the case, I argue, with the perihelion numbers that we discussed before. The mere fact that we have a bigger conjunction for the perihelion does not change the fact that one still holds P and not P. So the fact that it's a bigger conjunction, a bigger pair of sentences does not mean that the contradiction is not there. I'm saying that it's hidden, but it's there. Now consider this artistic illustration, it's mine. Since having in mind what I just said, consider this. Since I know that, So consider a person having a football. This guy here. Now consider the same person holding a non-transparent closed box in which there's a football inside. Would you say that the person has a football in the first case, but not in the second? In other words, does the mere fact that you cannot see the ball on the first glance, in this case, does this fact make any difference in whether the person in the second case actually has a ball or not? I would say no. The person holding the ball has a football whether I uncover it or not. So this person also has a football whether I see the ball or not. It's just the fact of the matter is still the case. And having this example in mind of this thing that you can see and this hidden thing which is still there, consider this. So to uncover or surface this contradiction, consider that one person X holds that P, person X holds that Q, then the third being Q necessarily implies not P, thus person X believes not P from propositions 2 and 3, and lastly therefore person X believes P and not P from propositions 1 and 4. So the mere fact that person X does not explicitly believe not P from 2 and 3 does not change the fact that he or she actually believes not P, holds not P. So in other words, just because the contradiction has to be uncovered with a little more analysis does not mean that it is not there in the first place. And just like the illustration, where the football is in the box, even if one cannot see it on the first glance, so is the contradiction there, even if one cannot realize or see it on the first glance. So this is the main idea of the hidden contradiction. This captures the main idea of the hidden contradiction behind Mercury's perihelion, but also behind inconsistencies in general, I might say. The main idea here being that an inconsistency is not less serious than a contradiction because an inconsistency hides a contradiction inside of it. The contradiction is there. So the implication, I argue, is the same. Since a contradiction in classical logic leads to explosion, so does the inconsistency in this sense of the word. Therefore, at least in relation to our discussion here, they ought to be treated the same. And the implications of this is the ones that I mentioned before. If we consider the superposition as being contradictory or being a case of a contrariety, then if those two things amount to the same thing, then maybe we can add on to that debate in that they should be treated the same. But I have to state that I'm a bit skeptical about that specific example regarding quantum superpositions. I think it's a bit different, but the idea is there. Yes, and now moving on. So having this thing in mind of the distinction between an inconsistency and contradiction, whether there is a distinction or not, I argued that there is no distinction. So now we'll move on to the main idea, being anti-exceptionalism here. I'm holding this idea. Science and logic go together. So as logic is not exceptional in this sense with respect to science, it is continuous with science, revisable, and even revisable following a scientific method. So I'm holding this assumption in this talk, and the main idea here being that the scientific method requires an underlying logic which governs the scientific reasoning. And could this, if we abide by this assumption, could this logic be classical logic? So could the underlying logic of scientific reasoning be classical? I'm a bit skeptical about that because of the aforementioned examples of inconsistencies in science. Because if the underlying logic is classical, then in the examples of, for example, Bohr's theory or the perihelion or other examples of inconsistencies, if the scientists reason with classical logic, then we would have seen a logical explosion. So their theories will prove anything and everything, but we didn't see that. So maybe the underlying logic was not classical and maybe it was actually consistent, whether they knew about it or not. Here I just want to stop for a minute and say a bit about consistency. So the previous discussion was necessary because if paraconsistent logics or other attempted solutions are devised with the aim of dealing with contradictions, then we need to be sure that what we are dealing with is indeed a contradiction. Now, many, if not most, contradictions in science are the result of false data, miscalculations, missteps, etc. But we do not always recognize what has gone wrong. So we need a way to deal with them safely until the contradiction is hopefully, say, resolved. And yeah, so one main disadvantage of these logics that other people argue as a disadvantage is that incoherence. If I accept a contradiction, then this will lead to incoherence. Contradictory claim will lead to incoherence. But I argue that this is not the case. Incoherence does not apply here. Accepting contradiction is inconsistency per se, but it is not, a contradictory claim is certainly consistent, but it is not necessarily incoherent. There is this paper by Priest, one of many papers that deal with this issue. So he presents in this paper an inconsistent story, and in the end he asks the question, does this story make sense? I mean, it is inconsistent, but it is coherent. So there is a differentiation between incoherence and inconsistencies. And yeah, since explosion is what turns a contradictory situation into an incoherent and unusable one, in this case, the inconsistent story or a story with inconsistent elements was still intelligible and thus coherent. And yes, now I want to move to this logic, this consistent logic that I want to be using, which is based on the three-value paraconsistent logic LP, well known by Priest. And yes, and this is a truth table. So the truth tables for the main it's conjunction, conditional material, and conditional negation. So we have here in this logic we have three values. So it's truth, both true and false, and false. So in these truth tables, the red values correspond to the paraconsistent logic, whereas the black values correspond to the classical logic. But I have to say that the paraconsistent logic, this logic is not a replacement of classical logic, it's just extending classical logic. So the black values here are classical values, whereas the whole truth table is the paraconsistent one. And I have to say that the two designated values here are true and both. So we have two designated values. However, both is, and I think Priest also admitted this in paper in 2014. So the both true value is technically not a third value, it is just a combination of the two. Holding this in mind, now I want to talk about the ontological or epistemic implications of this logic. So I want to say that this logic does not have the strict ontological commitment that Priest or Dialytis wanted to have. So my main idea here being that retaining an inconsistency in theory in science or reasoning with it does not necessarily imply that does not necessarily imply a contradictory object, phenomenon or world. So I want to take this logic as being epistemic rather than having the ontological implications. So again, as Priest put it, the use of paraconsistent logic does not commit one to dialectism. It did not. This is something that I have pointed out many times. Nor does using LP imply a commitment to dialectism either. So, in the case of Bohr's inconsistent atom, Bohr did not think that the atom was inconsistent, and the atom was not inconsistent per se, but the reasoning behind it considered the atom to be as such. So maybe the truth value, the third truth value, could be interpreted epistemically. Therefore, the logic would be a three-valued one for all practical purposes. It could be this case. And in other words, the B value, the both true and false value, does not necessarily imply that there's a situation in the world in which actually this situation being true and false at the same time. But still, I would say that we can use this three-valued logic as a tool, allowing the contradiction in the tool, but not letting it slide into the empirical world. And finally, the paraconsistent logics are independent of dialectism, as I mentioned in the quote by Christ before. And the main idea here being that dialectism, the view that there are true contradictions in the world, calls for paraconsistent logic, but not the other way around. And since dialectism is an ontological view, it's a view about the ontology of the world, and since the logic LP or paraconsistent logic in general do not necessarily imply dialectism, it means that we can use this logic epistemically, using paraconsistent logic as a LP in this case, as a tool that will ensure a non-explosive rationalist reasoning when reasoning with an inconsistent basis. So if the slide to dialectism from logic is avoided, then every time an inconsistency in scientific theory arises, it would force, let's say, scientists to believe that that specific phenomenon is not contradictory. It would not force them to believe that it's contradictory, because the tool deals with this contradiction without letting it slide into the world. And if many contradictions science are due to false data, as I said before, etc., then scientists will be ascribing to contradictory phenomena all the time, even though even priests realize that most of them are not doing so. So there would be if there was this slide of contradictions from the logic into the world, there would be an unnecessary inflation of contradictions, because every time we will have a contradiction in our theories of reasoning, then we would believe that this contradiction is part of the world. So we have all these inflation of contradictions. And this even goes against Christ's own ideas. So this idea of Christ's razor, which holds that we should not posit contradiction beyond necessity. So even he agrees that we shouldn't posit contradictions beyond necessity. And this would be the case if our logic was sliding into the world, if the implications of that logic were part of the world. But yeah, I have to stop here, and yes, thank you for your attention.